Hello students, good morning. Today we will discuss about the Ampere's law. In last lecture we have discussed about the Bio-Savart law. Now in this lecture we will discuss about Ampere's circuital law, or we can also say only the Ampere's law. We know that in electrostatic we have already discussed about the Gauss law. Then Gauss law is related to the distribution of charges. Then the distribution of charges over a closed surface can be find out by using the Gauss law, and electric field due to the distribution of charges is find out in electrostatic by using the Gauss law. And we know that the Bio-Savart law is related to the magnetostatics, and this Ampere's law is related to the magnetic field due to the distribution of currents, not distribution of charge, but it is the due to the distribution of currents. Now here the number of wires are shown. Suppose the wire, first wire, second wire, third wire and fourth wire, and the current passing through this wire. First wire I1, then current passing through another wire is I2, and current passing through third wire is I3, and then here is the one more wire that current passing through this wire is I4. And we have to find out a magnetic field at a point due to these all currents. Some of these currents, suppose this I1 and I2 are the currents which are coming out of plane of paper. I1 and I2 are the currents which are coming out from plane of paper. And here, because this symbol indicates that the current is coming out the plane of paper, and this symbol indicates the current going into the plane of paper. Therefore, I4 and I3 is the currents which are going into the plane of papers. Now we have to find the magnetic field at a point. Suppose here is a point, we have to find the magnetic field. Therefore, draw a loop, a closed loop which is passing through this point where we have to find the magnetic field. Draw a closed loop which is passing through that point where we have to find the magnetic field. Then this loop is called the Amperian loop. This loop which is passing through a point where we have to find the magnetic field, and this loop is called the Amperian loop. This is the direction we have to consider here of the Amperian loop. Suppose this is the length dl. First at all we will consider a small length dl, and then again we consider another small length dl, and the magnetic field at this point will be b. Then we can consider again a small length here dl, and magnetic field at this point will be b, and therefore we can consider a number of small lengths on this the Amperian loop. And to find the total magnetic field at that point, we can integrate this total magnetic field. We have to find the total magnetic field. Then we can find we can integrate the magnetic field due to a small length and all these small lengths. Then we must have to take a direction of integration, or we can say the direction of loop. This is the direction of integration, or also we can say this is the direction of loop. This is anti-clockwise direction. This is the anti-clockwise direction. Then this Ampere's law states that the magnetic field over a closed loop, is equal to mu naught times the total current enclosed by that loop. Therefore, by this Ampere's law, we can write here, this is the Ampere's law over a magnetic field over a closed loop is equal to mu naught times the current enclosed by that loop. Here, first at all, we are going to consider a small length, and taking integration of this equation, we will get the total magnetic field over a closed loop. This symbol is indicate that the loop is closed. This loop is closed. When we consider a point, one point, loop is starting from that point. Suppose this is a point and loop is starting from this point. We will consider a small length and number of small length. Then the loop will be end at this point. This is the closed loop. Therefore, integration over a closed loop. This symbol that is for the closed loop. Therefore, integration over a closed loop, the magnetic field at a point is equal to mu naught times the current, total current or net current enclosed by that loop. Now, we can say that here in this loop, some of the current is coming out of the plane of paper and some of current is going into the plane of paper. Therefore, to find the net current enclosed by this loop, we must have to take a sign for this current. But how we can take the sign for this current? Before going to taking the sign for this, we can use the curved palm right hand rule to find the sign of current. Now, this equation can be written as, or we can say that vector B into vector dl is equal to mu naught times the current. Current is the scalar quantity. Therefore, the product of these two vectors is the dot product. Because current is scalar quantity, therefore we can say that the product of these two vectors is dot product. Therefore, we can write here B into dl cos theta, where theta is the angle between magnetic field and length dl. Consider this is the small length dl and this is the direction of magnetic field, that is this is the angle between magnetic field and the small length dl. Then we have to take the integration of this equation over a closed loop. Therefore, we can write this equation can be written as B cos theta into dl. B cos theta into dl. It means that we can say this is the dot product of component of magnetic field in the direction of dl. Therefore, B cos theta into dl. B cos theta is the component of magnetic field which are tangent to the loop. B cos theta into dl. Now, to apply the Ampere's law, we have to know the sign convention for the current. This sign convention can be found out by using curved palm right hand rule. How to apply this curved palm right hand rule? Consider right hand. This is our right hand. This is our palm. And curl the right hand palm along the Amperian loop. This is the Amperian loop. This is the direction of this integration. Then curl the right hand along the Amperian loop with the fingers. With these fingers in the direction of integration. This is the direction of integration. And this right hand is curled in the direction of integration, or fingers in the direction of integration. Then the current in direction of stretched thumb, the current in the direction of stretched thumb is assigned as positive. Suppose this is the wire. This symbol indicates that the current is coming out the plane of paper. That is, we can say this is the direction of current or wire. This is the wire. And we can say this is the direction of integration. The fingers of right hand are directed in the direction of integration. Then this thumb will indicate the direction of current, and the current in this direction of stretched thumb is taken as positive. Therefore, the current I1 and current I2 are taken as positive because these two currents are in the direction of stretched thumb. Therefore, I1 and I2 are taken as positive. Whereas this I3 and this I4 are into the plane of paper, that is direction of wire, or this is direction of current, is into the plane of paper. Therefore, we have the right hand and the current in the opposite direction of stretched thumb. The current in the opposite direction of stretched thumb is taken as negative. Therefore, this I3 and I4 are taken as negative. I1 and I2 are taken as positive. This is the curl palm right hand rule. So here I will again discuss the curl. The right hand palm along the Amperian loop with a fingers in the direction of integration. Then the current in the direction of thumb the current in the direction of thumb will taken as positive or assigned as positive, and the current in opposite direction of this thumb is taken as negative. Therefore, from this we can say that, or we know that by the Amperes law, the integration over a closed loop into dl is equal to mu naught times the total current. Then when we take in the total currents, this equation can be I is equal to this I1 plus I2. I1 plus I2. This I1 and I2 are positive, therefore I1 plus I2 minus I3, because I3 is assigned as negative. Therefore, the total current or net current enclosed by the loop is equal to I1 plus I2 minus I3. This is the net current due to the wires in the loop. This I4 is not considered here. This I4 is not considered here because this I4 is out of this Amperian loop. This I4 wire or current I4 is out of this Amperian loop or this closed loop, and therefore this is not considered here to find the magnetic field to pass through a point, and and the point or this loop is drawn going through this point, and this current is out of this loop. Therefore, this current is not considered here. And we know that the magnetic field over a closed loop, here is over a closed loop, is equal to mu naught times the total current enclosed by that loop. Therefore, the total current enclosed by this loop is only I1, I2 and I3. This I4 is out of loop, therefore not considered here. And this equation is known as the Amperes equation. This equation is derived from the Amperes law. By using the Biot-Savart law, we can prove this equation of Amperes law. Then we will use the Biot-Savart law to prove this equation. Now, consider a straight wire. I is a current passing through this wire. Consider a straight wire. I is current passing through this wire. Now, consider a Ampere loop around this wire. This is the direction of loop. Now consider a point. Here we have to find the magnetic field. Now draw a small length. This is the direction of length dl. This is the angle. We can say that d theta, and this is the direction of magnetic field or component of magnetic field. Then we can say that, or we know that the B, the dot product of two vector B and dl is equal to B into dl cos theta. Here theta is the angle between B and dl, and the direction of magnetic field and length is in the same direction. Therefore, also we can say this is the direction of magnetic field and this is the direction of magnetic field and dl, which are in the same direction. That is, we have to take a tangent to this circle. Therefore, B and D are in the same direction, and therefore the theta will be equal to 0. Therefore, we know that the cos 0 is equal to 1, and therefore B dot vector B dot dl is equal to B into dl. Now, here small length dl and this d theta is the angle made at the point or at the center of this circular loop or Ampere loop. That is the d theta, the angle made by the dl at this center of Ampere loop is d theta. Therefore, we know that the dl is equal to, and the length dl is at a distance r from this point O or center of this Ampere loop. Therefore, we know that, but dl is equal to, here we know that dl is equal to r into d theta. dl is equal to r into d theta. Therefore, we can write here B into dl is equal to b. Put the value of dl, therefore b into r into d theta. Now, by using the Amperes law, that is current passing through a straight conductor. A current is passing through the straight conductor and magnetic field near this conductor is given by the equation B is equal to mu naught I upon 2 pi r, where I is the current passing through this conductor and r is the distance, where we have to find the magnetic field from this conductor. Therefore, we have already discussed or derived or we know this formula, that current passing through conductor and magnetic field at a point near the straight conductor, and therefore B is equal to mu naught I upon 2 pi r. Therefore, we can put the value in this equation. Say equation 1, put this value of B in equation 1. Therefore, we will get B into dl is equal to B. Value of B is taken as mu naught I upon 2 pi r into r into d theta. Now, we have to take a total magnetic field over a closed loop. Therefore, taking integration over a closed loop, loop is closed. Therefore, this symbol is shown here. B into dl is equal to integration on this right side mu naught I upon 2 pi r into r d theta. All these quantities are remain same. Therefore, we must have to take the integration of theta d theta. Therefore, we can take the limit 0 to 2 pi, because this is the angle d theta and we have to take the integration of this angle from 0 to 2 pi. 2 pi means the whole angle of this here. Now, we can here this equation can be written here. B vector B into dl is equal to, taking these all terms out of the integration, therefore we can write here mu naught I upon 2 pi r and this r, and taking the integration of d theta, therefore d theta limit as 0 to 2 pi. Therefore, this equation will become, this r will cancel here, mu naught I upon 2 pi, and the integration of d theta at each and every time this d theta plus d theta plus d theta will be equal to total angle of circle, that is the theta. Therefore, limit is taken as 2 pi, 0 to 2 pi. Therefore, putting the value of limit theta, this will be equal to 2 pi. This 2 pi will be cancelled. Therefore, this will equal to mu naught r. That is integration over a closed loop of magnetic field. B into dl is equal to mu naught times r. Therefore, by using the Amperes law, we can prove the Amperes law, and this is the Amperes law, that is magnetic field at a point, or taking the integration of over a closed loop, the magnetic field at a point is equal to mu naught times the total current. Here I is the total current enclosed by that loop. Now we can say that, or we have already discussed or studied the Gauss law in electrostatic as well as magnetism. This equation shows that the distribution of current has high degree of symmetry, such as cylindrical symmetry in case of long wire. Then the magnetic field for a given distribution of current can be easily calculated. We know that Amperes law plays the important role in the magnetism, or we can say magnostatic, as well as Gauss law plays the important role in the electrostatic. Gauss law is related to distribution of charges, and this Amperes law is related to the distribution of current. And this is the equation derived by using the Amperes law of the Amperes law. Okay, thank you.